Okay, on to the serious talk of the evening. Science of Santa. We're asking ourselves, is Santa compatible with the laws of physics? Or if you turn that around, just how many laws of physics does Santa actually break? We know what he's supposedly capable of doing. Santa is, allegedly, a portly, jolly fellow with a white beard and a penchant for wearing red suits. And despite displaying questionable fashion sense, that doesn't mean he cannot exist. And the question is, what about the claims of what he's supposedly able to do around Christmas time? The statement we're looking at is this one. He visits, allegedly, all households on Christmas Eve to deliver presents to all qualifying children. And what is the qualification? Well, that's defined by his naughty nice list. Can we reconcile this amazing statement with our understanding of science and the laws of physics? And what got me interested in this was, well, is there anything I've described in the science of the other talks that I've given that actually help us? Is there anything in, this is a small selection of the talks I give, is there anything in here which helps us understand how Santa might be able to do the rather incredible things that are attributed to him? So that's what we're doing. We're taking this statement and we're going to unpick it one word at a time. That's the statement. Santa visits households on Christmas Eve to deliver presents to children. And we're going to not take them in strict order. We're going to jump around a bit to see what makes sense. So we're going to start actually with the last one and ask ourselves, okay, if he visits children, just how many children does he have to visit? Okay. How many children get presents at Christmas? Well, the Earth's population is 8 billion. Scary but true. 25% of those, I believe, are children. And how many of those get Christmas presents? I'm not sure, but let's assume for the sake of argument, half of the children in the world are eligible for Christmas presents. That might depend on the principal religion of the household, but Santa is generous even if they're not Christian. So about 1 billion children will get Christmas presents. That's assuming that the naughty nice list, let's just assume that no children are on the naughty list and all children are on the nice list. Parents might argue with that, but again, just to keep the numbers easy, let's assume it's a fair fraction of 1 billion children get Christmas presents. Okay, so that's dealt with how many. Now, Santa apparently visits all of these children. So how does he get around? What's his prime mode of transport? It's a sleigh pulled by flying reindeer. Okay, so the first question we can ask ourselves is, well, can reindeer fly? Well, we know that insects fly. We know that birds fly. We know that pterosaurs fly, though you don't see many of them these days. And we know that mammals fly, or at least some mammals fly. So what about reindeer? Well, if reindeer can fly, then they apparently choose not to do so for a lot of the time. There is very little evidence for flying reindeer. But remember, a good scientist should be careful about evidence. Absence of evidence is not the same thing as evidence of absence. So just because we can't produce photographs of flying reindeer, it doesn't mean they can't. So the jury is still out on whether or not reindeer can fly. How fast would Santa have to go in order to carry out these feats? To visit 1 billion children in one night, remember that's not simply 12 hours on average, more in the northern hemisphere, less in the southern hemisphere, because Santa can use the time zones around the world and he can stretch it out to about 36 hours or so. If he wants to visit 1 billion children in one night, if we assume the children are distributed across the land masses of the earth, many of them all in the same sort of places in big cities, he would have to travel at about 2,000 kilometers per second. But that's not a problem according to the laws of physics. That's just a tiny fraction of the speed of light, and that's the only speed limit that applies in physics. So if Santa moves at less than 1% of the speed of light, he's in no danger of defying any laws. In a talk I give on Fiat Lux, I actually measure the speed of light and actually show that it's about 300,000 kilometers per second. No object can travel through space faster than light can travel in a vacuum. It's a different situation when we're thinking about how the universe is expanding. The universe can expand, the space between galaxies can expand as fast as it wants to, and that indeed is expanding faster than the speed of light. But in terms of objects moving through space, we have this speed limit, and Santa is well under that speed limit. But if he's moving really fast, wouldn't he heat up and we'll end up with roast reindeer? Well, we know that as meteors, effectively small rocks, or asteroids, big rocks, entering the Earth's atmosphere, as they come into the Earth's atmosphere, they compress the air in front of them, and that compressed air heats up. Now, we know from our understanding of stellar evolution, and when I talk about the ABC of stellar evolution, the C stands for compression produces heat. When the middle of a star gets compressed, it gets hot, and eventually it gets hot enough for nuclear fusion to occur, and that's how stars effectively are born. So we understand that, yes, objects that are moving through the Earth's atmosphere will undergo compression of the air, and the compression will produce heat. Even if the sleigh is aerodynamically designed, it will still get hot. And then you have a problem. If this object is really hot, the sleigh and Santa and the reindeer, if they're moving that fast, won't they be glowing white hot? Shouldn't it be easy to see the sleigh on Christmas Eve, because all you would need to do is to glance up at the sky and you'd see a huge white hot object flashing around the sky. So if you ask, shouldn't the sleigh be easily visible? Well, you could say maybe it was, though it's pushing things a little bit to claim that the Star of Bethlehem was actually Santa's sleigh, because surely the timing isn't right. If the Star of Bethlehem appeared at about the time that Christ was born, how come Santa is already going around the world delivering Christmas presents? So rather than being the Star of Bethlehem, maybe this bright light in the sky, many people would argue, is easily visible. Not necessarily on Christmas Eve, but at other times of year you do see bright lights in the sky. But there is an alternative. What do we know about that even when it gets hot does not emit light or reflect light or even absorb light, or indeed any other type of electromagnetic waves? Well, we know it's out there. Dark matter. Most of the universe's matter is dark matter rather than ordinary matter. If Santa and his sleigh and the reindeer were made of dark matter, then even if they did get hot, they would not glow. An ordinary lump of material, if you heat it up, gets red hot, and you heat it up some more, it gets white hot. But that's not how dark matter behaves. So maybe that explains why we don't see Santa's sleigh as a white hot object moving through the sky, because it's made of dark matter. That would also explain why it doesn't show up on radar as well, because radar would simply go straight through the sleigh and would not reflect off it. So we've dealt with children and we've dealt with transport and Santa visiting. What about the households that he has to visit? How could Santa get down so many chimneys so quickly? If you want to visit 1 billion children in one night, Santa would have to squeeze down thousands of chimneys each second. And remember, Santa is a portly gentleman, maybe 1.5 meters or so high, but almost as much in the girth as well. So how could he possibly get down a chimney? Well, the quantum theory of how things behave on very small scales gives us a clue. We know that pretty much everything is made up of molecules and atoms are made of a nucleus surrounded by a buzzing set of electrons. If you were to replace the electrons in an atom with a heavier particle called a muon, which is a bit like a heavy version of the electron, the atom would be some 200 times smaller. And that means anything made of those atoms would also be 200 times smaller. So if you make a Santa out of atoms in which you replace all the electrons with muons, instead of being 1.5 meters tall, Santa would be barely 1 centimeter or so high. And he would fit down a chimney, no problem whatsoever. So I don't know quite how Santa would replace all of his electrons with muons, but if he did, that would get him down chimneys with no problem whatsoever. But you say, hang on, not all houses or apartments have chimneys. So how could Santa get inside when there's no obvious form of access? Well, quantum theory comes to our rescue one more time. We know that when we look at things on a small scale, it is possible for a particle to go from A to B, even though there's a barrier stopping the particle going from A to B. Much like Santa's on the outside of a house and he wants to be on the inside of a house, but there's a wall stopping him and none of the doors and none of the windows are open. But if quantum theory, or quantum mechanics as it's sometimes called, tells us that it is possible for a particle to get through a solid object, so-called tunnel through it. It doesn't mean taking the bricks out of the wall and then going through the gap. Santa, in principle, can pass straight through the wall using the same laws of quantum mechanics that allows particles to tunnel through barriers that, according to good old-fashioned Newtonian physics, they should not be allowed to do. So maybe that's how Santa does it. So we've thought of children and visits and households. Let's have a think about how he does all of this on Christmas Eve. He does this all in one night. How can he make so many deliveries all in one night? Even if he's travelling at relativistic speeds, a fraction of the speed of light, in between each delivery, how can everything be done in 36 hours? Well, according to quantum theory, again, quantum theory is very handy here for explaining various aspects of Santa. We know that when we look at the world on a scale that's very, very small, we know that particles can be in two places at one time. Doesn't seem to make any sense in the real world that we see around us. If we're having a look at the cup of tea on the table in front of us, it seems to be in one place. It doesn't seem to be in two places at the same time. But when we look at what electrons are doing and what nuclei are doing and what atoms are doing, they do seem to behave as if they can be in two places at one time, or maybe three places at one time, or 4 or 1,000 places in one time. So if it's possible for a subatomic particle to do this, and Santa is made of molecules which are made of atoms, which are made of subatomic particles, then why can't Santa be in two places at once as well? That, of course, makes his job a lot easier, because if he can be in 1 million households at the same time, then he doesn't have to visit them all one at a time. If for some reason you don't like that and you think that Santa should only be in one place at one time, then he would need some alternative way of making those deliveries. Maybe he can distort space and time. We know that's possible because Einstein's general theory of relativity tells us that mass changes space and mass changes time. It's very counterintuitive, which is why it took a genius like Einstein to come up with the theory, but that's apparently the way the universe works. Mass does distort space and it does distort time. Maybe Santa has figured out a good way of doing that, such that he can distort space and time to allow him to make the deliveries across billions of children in 36 hours. So we've thought about children and visits and households and Christmas Eve. And finally, we have to think about how he can deliver lots of presents to these children. So how could he carry all of these presents? How big must Santa's sack actually be? One present for each of 1 billion children? How could the sleigh hold that many? Well, yes, it could, if you warp space in such a way that the inside of the sleigh is bigger than the outside. And to have an object which is bigger on the inside than the outside is not simply the realm of Doctor Who's TARDIS. That is precisely what happens with a black hole. If you look at the physics of black holes, they are bigger on the inside than they are on the outside. So if it's possible to distort space to allow that to happen, again, maybe Santa has figured out a way of doing that with the sleigh. So although the sleigh only appears to be a few meters in size, maybe it's a lot bigger on the inside. Again, if you don't like that, well, maybe there's an alternative way that he does that. We think that the universe is made with 3 dimensions, forward, backward, left, right, up, down. But there's plenty of physicists who say, no, there aren't just 3 dimensions, there's lots of dimensions, more than 3. maybe Santa has figured out a way of accessing these other dimensions. In which case, you simply take all the presents, somehow you push them out of our 3 dimensions and into one of the other dimensions, then you go about your business, you visit the various children, and one by one you pull those presents out of the other dimension back into our dimension and put them under the tree. So that's an alternative to distorting space and time. Both of them effectively rely on theories of how we think the universe works. But you might say to yourself, okay, that's all very well, but wouldn't everything you've described up till now require a huge amount of energy? If Santa and the sleigh and 1 billion presents are moving at relativistic speeds, wouldn't that need an incredible amount of energy? Well, yes, it would. But maybe the sleigh is powered by, for instance, a black hole. We know that black holes produce enormous amounts of energy, so why is it not feasible that the sleigh is powered by a black hole? Hypothetically, a black hole could power a starship and send you to the nearest star in a time frame that would allow you to get there apparently in only a matter of days. But we are overlooking something. We are overlooking the fact that there's an energy source, the elephant in the room, the one thing we haven't mentioned yet, which is a source of a huge amount of energy. What happens to all the mince pies? If households leave a mince pie for Santa, surely nobody is naive enough to believe that Santa eats them all. No way could he eat millions of mince pies. That's just crazy talk. What if Santa could convert the mass of all the mince pies into energy? Again, thanks to Einstein, we know the equivalents of energy and mass are given by the equation E = mc squared. If we know the mass of an object, if we multiply it by the speed of light squared, we get the energy equivalent. In essence, we get the energy that we could, in principle, extract from that object. So what if Santa has figured out a way of extracting the energy from a mince pie? How much could he get? Well, let's do the calculation. 1 mince pie is about 50 grams. So if we multiply 50 grams by the speed of light squared, we get an energy from 1 mince pie of 5 times 10 to the power 15 joules. I'll come back to how big a joule is in just a moment, but that's the energy that physicists use. Sorry, that's the energy unit that physicists use. First, let's work out how many mince pies. Well, if we assume just a few % of households leave a mince pie for Santa, let's assume that more than 90% of households don't bother with that. Then if we take a few % of households and then multiply that by 1 billion households and then multiply by the energy of 1 mince pie, we get 20 million mince pies or thereabouts. Multiplied by 5 to the 15, we get a total energy available to Santa of 10 to the power 23 joules over the course of the night. Now, given that you can't easily imagine what that energy is, let me put that into terms we can understand. If you imagine the output of a nuclear power station, a gigawatt power station, and not a gigawatt power station that's running all night, imagine a gigawatt power station that's running for 1 million years. That energy is the energy available to Santa in one night. That is a huge amount of energy. That's easily enough to do the sort of things that I've been talking about. So how would you extract E = mc squared from a mince pie? Well, there's a couple of ways you can do it. The most efficient way of extracting energy from matter is to take a lump of matter and take a lump of antimatter and collide them together. So in this case, you would collide them together in the Large Mince Pie Collider at CERN. But of course, that relies on the fact that somehow you have to find yourself an antimatter mince pie, an anti-mince pie. So that would be very efficient, but there's no obvious way you can get hold of anti-mince pies, so maybe that doesn't work so well. Is there an alternative way to extract a reasonably large fraction of most of the E = mc squared energy from a mince pie? Well, yes, there is a way of doing it, and it might be an answer that we've already mentioned. if you drop the mince pie into a black hole, it will release an enormous amount of energy. So, for instance, if the sleigh is being powered by a black hole, all Santa would have to do is throw the mince pie over his shoulder, and that would release a huge amount of energy. Now, we know that matter falling into black holes does produce an enormous amount of energy. A quasar, the center of a very energetic galaxy, has matter, probably not mince pies, it's probably gas and dust and stars falling into the central black hole. And we know that produces enormous amounts of energy because, as was mentioned earlier, even without a telescope, it's possible to use a camera to image one of these quasars, even though they're at a distance which is effectively on the other side of the observable universe. That tells us the amount of energy that you get from matter falling into a black hole is absolutely vast. How much would you get for a mince pie falling into a black hole? I couldn't find any research being done in this area. I could not find any publications giving me numbers as to how much energy is released. I'm assuming it's a fairly large fraction of the total energy, E equals mc squared. No reason to assume otherwise. So plenty of energy available to Santa. If Santa is capable of warping space and time and controlling black holes, how does he do all of that? They may be allowed by the laws of physics, but how can Santa manipulate space and time apparently so effortlessly? Well, one thing we have to bear in mind is nobody has actually seen Santa because everybody's asleep when he visits. So how do you know that Santa is human? Maybe there's an alternative. Nobody actually knows the skin color of Santa. So perhaps there are people or beings that can control space and time. So, to come back to the original question, how many laws of physics does Santa actually break? When you work all the details out, you find that the answer, I think, is none. So feel free to draw your own conclusions about the existence or otherwise of the portly, jolly fellow with a white beard and a penchant for wearing red suits. And regardless of your conclusion, for a second time this evening, I wish you all a very Merry Christmas. Thank you.